increases in strength as you progress through that training program. The more trained you get, the more you have a contribution of size to the change in strength, right? Because when you think about it, we do a resistance training session, muscle protein synthesis goes up post-exercise, yes? Right, so signaling activities, transcription factors, ribosomes get together, protein synthesis goes up after that session. It goes back down to rest, right? But that goes up slightly, maybe it's elevated at rest for a few, maybe a day or so, but then if you're not working out, it goes back down to rest. So it takes repeated sessions to accumulate that protein synthesis into a larger muscle. So yes, larger muscles, larger fibers do produce more force. But here, we've done maybe 6 or 7 workouts, so we haven't accumulated enough muscle protein synthesis and contractile proteins yet to make the fiber significantly bigger to be able to add to that force. But when we look at 4 weeks into the training program, the fibers and the muscles have gotten larger. So now that we've added more fiber size, more contractile proteins, on top of the EMG activity being high as well, both of those then contribute to the addition of strength. Does that make sense? If we think practically, someone who's untrained, they get into dumbbells or barbell, they do a bench press, and they're like, I'm the bench press, and they're like, the weights are going all over the place, they're like, wacky wild inflatable tube world, Family Guy, you know that guy? Okay, this is what I was saying. Anyway, so it's all discombobulated and organized, and coordination is not very great because they don't know how to recruit those motor units, coordinate the activation of the muscles, agonists, antagonists effectively. So therefore, the movement is not effective in producing force. But if you notice, even within a few workouts, if someone keeps showing up to the gym, the movement of them doing those exercises increases and gets better pretty rapidly. And again, that's because the muscle is able to adapt neurologically to produce force much quicker to increase strength compared to having taken so long to add the muscle fiber size, right? So key point, don't get this confused, because on your exam, the early adaptations in strength to training are largely neurological, okay? Later on, it becomes more hypertrophic. Now, in this study, they had 2 different exercise intensities. They had a 30% 1RM, and then they had a 80% 1RM. Now, if you remember, in the last lecture, we said, okay, when they did those repeated contractions to failure, there was a difference in muscle activation at the start of that set versus at the very, very end of that set under fatigue. Muscle activation was very different, wasn't it? Like the EMG activity at the start of the set was like this, and then the EMG activity at the end of the set was like this, right? Because fatigue, they require them to recruit more motor units, the motor units are more active, and so to maintain that force. So we know that if we're fatiguing, we're probably going to be recruiting some more motor units to try to maintain the force. And so the hypothesis was that, okay, you can do low intensity resistance training and increase muscular strength and size. And that's true. Even loads as low as 30, 40% 1RM, muscles will get bigger, muscles will get stronger, provided it's to failure, okay? So that exercise sets have to be to failure. With higher loads, you don't have to go to failure to see an increase in strength because the load is really, really high, which is activating the neuron. But the low intensity, you need to go to failure to cause or create enough stimulus with such a low load. All right, so the idea was that, okay, well, why is it that muscles can grow with such low loads to failure? And their hypothesis is because, well, as the muscle fibers fatigue, maybe you're recruiting more motor units, those more type 1s and type 2As and 2Xs, to recruit more of them, so that results in increase in strength just from going to failure. But when they did a study and they looked at 4 sets to failure with each of these intensities, we can see that obviously the condition that they had low loads, they had to do way more reps to reach failure within each set. Both conditions did 4 sets, so set 1, 2, 3, and 4, okay? If you look at the volume performed with each condition, the lower load, they did more reps, right? Obviously we know lighter weights, you can do more reps of them, right? So to get to failure at that load, you have to do a lot more reps, whereas heavier loads, they're harder. You do less reps with them. right? You can't do a 1 RM for 10 reps. It's just, that's not the definition of 1 RM, right? So we know that. Force has a limit depending on the number of reps you do. But the common factor here is that in every set, they went to failure. So if we're thinking about the investment of effort between 30 and 80%, what's being matched here? They're both doing 4 sets, and all of those sets are being done to maximum volitional fatigue, right? So at least that's consistent, even if the loads are different. But what do we see that if you look at EMG amplitude, even though the 30% condition went to failure every single set, the overall muscle activity, EMG amplitude, was always consistently higher in the 80% condition, right? So this kind of goes back to when we look at that failure slide at the end of last lecture. It was like, oh, well, they went to failure, greater muscle activity. Okay, that makes sense. But we can see that even if you do light loads to failure, you're still not getting the same overall muscle activity compared to a heavier load to failure, right? Now they said, okay, well, what about, is there a difference between at the start of the rep or the end of the rep or of the set or the middle of the set? You can look at every single set. In set 1, the first rep versus the middle rep versus the last rep, every single point along that set, EMG activity was always higher in the higher load. In the second set, in the third set, even on the last set, again, consistent. So it doesn't, this would, you might suggest, oh, well, what about at the end of set 4? Was, this is the very, very end of that set. Is 30% EMG match 80% EMG? Still, no, right? So the idea here is that this is one of the tenets as to why when you do really load resistance training, the muscle can get bigger and the muscle can get stronger. But the muscle will not get as strong compared to if you did a program that used heavier loads, right? Where have we heard this kind of concept before, right? You get the strongest when you lift the heaviest.
Fibers.
So, what was I?
Fibers. What do you equipment of fibers?
Well, that's one of the mechanisms, right? You get stronger because when you train with heavier loads, you're recruiting more of those bigger motor units, right? But this is talking about specificity, right? You can lift low loads, get bigger and stronger, but heavier loads, you get the most strong, right? So the adaptation is specific to the way that you're training, right? If you're lifting heavier loads, you need to use more force, more strength in that workout. That results in better strength, right? What's the concept? Yes? Yeah, specific adaptations to impose demands, right? Because the heavier load workouts require more recruitment of motor units, recruitment activation of more muscle, that develops strength more specifically compared to a workout that still recruits muscle fibers. They still get stronger, but it's not training the highest threshold or the biggest, strongest fibers or motor units in a way that optimizes strength. Okay, so why are we talking about this? Because if you look out in the literature and you say, well, what's the best way to train for adaptation? You can find literally thousands of articles suggesting how to work out this way, how to work out that way. But it really kind of just depends on what your goals are, okay? If your goal is, I just want to get bigger, then you could lift low loads to failure and get just as big as heavier loads to non-failure. But if your goal is to maximize strength, you can't do the lowest loads to failure all the time, because even though you might get a little stronger, you wouldn't get as strong as if you had done heavier loads. Now, why does this matter? Because if I'm a strength coach and I know that I'm going to get my athletes, I'm a strength conditioning coach and I'm working with the soccer team or the football team, and I'm only going to get my athletes for 45 minutes 3 times a week, right? I've got less than 150 minutes to get get this training in with them per week, right? So now I have to think about how am I going to implement this training to get them the most adaptations in the shortest amount of time, okay? If you're a strength coach and you're not focused on your athletes getting bigger, but you want to emphasize power and strength, then you have to periodize your program to have periods where you are lifting stronger, right? Lifting higher forces to develop that strength to complement power later on, right? Or if you want to add get your athletes bigger and stronger, well then you'd want to have sets and rep schemes that are developing both strength and size at the same time. Okay? But if you're like a bodybuilder like Ronnie Coleman or Jay Cutler, it doesn't matter how strong they are. They just need to get the muscles as big as they possibly can. So if you look at bodybuilder type workouts, besides the fact that they take all kind of anabolic steroids and illegal substances, their workouts are extremely high volume, right? Very, very high volume, because what they've shown is that the growth of the muscle fibers really depends on how much volume you're doing of that muscle group in a week. Right, so whether you do 32 sets of a muscle group on one day, or you split it up between 2 days, right, 16 and 16, or you split up between 3 days, right, 8, or 40, 8, 8, right, 24, another 8, 4 days, right? You could split up between a week. At the end of that week, it doesn't matter. Whatever volume you did is going to result in similar adaptations. The less volume you did, the less increase in size, okay? So on one hand, it gives us variety in how we can design our training programs, but also it makes us understand, okay, if I want a specific type of adaptation, I need to train in a certain way to get that, okay? The other flip side of this benefit, if you're elderly, and we know that muscle mass is a significant predictor of quality of life as you age, right? So if you have more muscle mass, and if you are stronger, and as you age, you are going to have better activities of daily living and quality of life, right? Maybe not longevity, right? But the quality of life as you live is going to be better. So if you're elderly, you might think, well, I want to try to make sure I can maintain some muscle mass, but it's hard because sarcopenia, reduction in anabolic factors. But if I want to maintain strength or increase strength, I could do a variety of types of workouts to increase strength. But ultimately, the best increases in strength would be from lifting heavier loads. Now, do you have to do 1RMs? No. But you should know, if you're a clinician, maybe you should encourage them to try to lift on the heavier end of that spectrum, because that's where they're going to get better adaptations in strength, which might transfer to their activity of daily living better than just doing little soup can shoulder raises, right? Probably not enough resistance. Lots of reps, maybe a little stronger, but not going to really have much transference versus like doing, a shoulder press with dumbbells or something like that with heavier loads. Does that make sense? All right. So ultimately, we see that both of these conditions, 30 and 80, they went to failure, but overall muscle activation was at fatigue was higher with the heavier loads, okay? And so that's where the thesis around, if you want the best adaptations in strength, you need to lift heavier loads, because clearly it activates the muscle more. Now what's interesting is that there was another study that they compared heavier and lighter loads in lots of research studies. But in this study, they decided to look at muscle activation with heavy and light loads, but they also looked at use of substrates in the muscle fibers. So we can see, just like the other article, that when you did heavier loads, 80%, there was a greater EMG activation, both at the beginning of the sets and at the end of the sets, compared to a 30% intensity, right? Both higher. So that's consistent, what we just saw in the previous slide. But what's interesting is that when they looked at the use of muscle glycogen in type 1 and type 2 fibers, right, which muscle fibers are going to be used preferentially in high load or high force activities?
2X.
Type 2, probably 2X and 2A, right? But primarily the 2s versus the 1s. So if we look at the EMG, we would say, oh, if there's more EMG activity with the heavier loads, you would think to yourself, oh, the type 2s are activated more, right? Which substrate do the type 2s preferentially use? Carbohydrates, glycogen. The type 1s use more fats, they're oxidative, right? So if we're looking at this data and we say, oh, the EMG is higher with the heavier loads, then that might suggest I'm using my type 2s more. So if you looked at the glycogen between the low load and the high load in the type 2s, you might expect the type 2s to use more glycogen in the heavier loads, because those fiber types are used in the heavier loads. But what's interesting is that when you look at the actual glycogen use in type 2 fibers between the two intensities, there was no difference in the glycogen use between the heavy load and the light load in type 2 fibers. Okay? So that essentially says that whether you did heavier loads or light loads, the use of glycogen in type 2 fibers was the same. So you might think, well, if the EMG was not as high in the low load, how were they using the substrate in the type 2s, right? Remember the size principle? You don't recruit motor units and muscle fibers unless there's enough force to turn them on. So if 30% is not activating the muscle as high because EMG is not as high, how were we able to use the substrate in those fiber types if we didn't activate those motor units? The authors actually scratched their head in this paper. They were like, well, actually, they kind of hypothesized, well, maybe you cycle through motor units. Maybe the type 1s turn on and you turn on the type 2s for a little bit and then they turn off. And so maybe the overall EMG is not different, but you're cycling through. That was their hypothesis. It's been proposed by other researchers too. Maybe there's this kind of cycling phenomenon between the motor units, but it's not really well proven, but there may be part of the equation. We don't really know for sure. But my thought is when I look at this data, I think, well, if we think about the size principle, and we are talking about muscle fiber types, the 3 fiber types, which fiber types are we going to use first at low loads? Type 1. And then as the loads increase, what's the next fiber type we're going to use? 2A, and then the next fiber type at the heaviest loads? 2X, right? So you have 1s, 2As, 2Xs. But if you're grouping the 2As and the 2Xs together, now, like, if you're doing really heavy loads, you're using more of the 2Xs. If you're doing lighter loads, you're doing more of the 2As. So, but if you group them together, it's not possible to see which of those fiber types are being used more. If you did low loads to failure, maybe it's possible you were using more of the glycogen in the 2As and less of the 2Xs. If you're doing the 80%, maybe you were using more of the glycogen in the 2Xs. And so at the end of the day, use the same amount in the A's, same amount in the X's, the difference in the type 2s is actually the same, even if the activation of the motor units or fiber types were different. But you don't know that because you didn't separate based on the fiber type. This just says use the same glycogen in type 2s. But there's not just type 2s, there's 2As and 2Xs. So we don't know if maybe they use more glycogen in one of those fiber types versus another, right? So that's kind of a limitation, and that's kind of some other hypothesis they had proposed too. But I put that out there because, yes, we do know that heavier loads generally result in bigger increases in strength, and you can get pretty equivalent changes in size between a variety of loads and volume, provided there's more volume. But at the end of the day, there are questions about the training strategies and how we're recruiting motor units that doesn't always translate to like a clear answer on how things are working, right? So I kind of put that out there just to show like there are still some questions on even this topic, right? Like why would we use the 2X glycogen if we're using a intensity that doesn't really activate the muscle fiber? Like that's like a little bit of a disconnect there, right? But that's part of research, try to get to the point of or root of those questions. Yes?
What if you were just more reliant on PCR?
It's possible. That's also another possibility too, right? If you're doing less reps and it is high intensity, it's very possible that they use maybe more energy from the PCR system and use less glycogen because maybe they fatigue at the point that they would start using glycogen. That's a totally valid explanation too, right? But they didn't look at PCR, unfortunately, right? So we're limited in depending on like what they actually measured. But ultimately, if this is how science works, because if you notice that and you're like, oh, that's interesting, then if you were doing research, you might actually conduct that study again, except this time you'd look at PCR, or this time you'd do the glycogen based on the 3 fiber types instead of just the 2. And that's how we advance our knowledge in that field. So when we're writing our lab reports, right, think about like, okay, I have this result, this is what I found, this is this other study and what they found. The results can agree or they can disagree. There's no right or wrong answer. The results are the results. But what you should do is go through the methods, read through parts of the discussion of those other papers that you're comparing to, and see what they have to say about explaining the results. Because in all likelihood, you might find some justifications that might kind of also fit what you think is possible too. Okay, so I just want to put in a little thing there about the lab reports because on the first labs when students submit them, I don't think they realize how much the discussion actually matters. So you want to make sure that it's 10 points out of 25, almost half the grade is just in discussion. So you really do want to make sure you're taking your results, comparing to published studies, and just kind of interpret it, try to draw some distinctions and write about it. okay? That's the more important point to get there, okay? Not that you have to know the final answer, I just want to see, are you thinking about it, right? Do you have an idea of what's going on? And that's pretty important, right? So, who's ever thought like, okay, when you're lifting weights, who's ever heard of like, okay, the mind-muscle connection, right? You really focus on really thinking, contracting the fiber, greater force production. There is such a thing as concentrating to enhance force production. That is actually true. But what if I told you that not just force production, what if I told you just the intent to move forcefully or to move quickly, that alone is enough to activate muscle fibers in a way that is if you were actually contracting and producing force, right? When a muscle produces force, it's literally active potential being sent, it's resisting that force. As you are overcoming that force, the muscle's developing force to move that object, right? And that comes from the muscle being activated. But what if I told you that if you had a resistance, you were like doing a knee extension, except it was isokinetic, and every time you went to kick, it actually moved faster than you did, right? So it's like you think you get into a knee extension device, right? If you go to kick it, but it's such a low load, your leg has to move really fast to try to apply force, right? But it moves so fast through the movement that you actually don't apply force because it's such a light load, right? Did you guys cover this in 346 with the force velocity curves? So when a muscle's contracting at heavier loads, the reason why it produces more force is because there's more time for overlap, right? Think about it. Actin and myosin have time to overlap. They have more time to develop force, right? So when you are lifting heavy loads, the muscle's moving slowly, not because it wants to move slowly, but because it needs to move slowly to produce a lot of force, right? From the cross bridging, okay? But it's not intentionally moving slowly, right? You wouldn't intentionally move slow on high force. But at lighter loads, you move faster through movement, yes? You move faster because it's slower, but because you move and contract faster, there's less time for actin myosin overlap. They attach and detach, but as they move through that sliding filament, there's less time to actually develop force. So when you look at this, in one condition, they allowed the participants to develop force. This arm actually resisted them. So they were able to apply and push force, apply torque throughout the movement. Torque goes up. You apply force, torque goes up, movement goes up because of muscle activation. But in this case, it was isokinetic. So they had them move at a very, very fast speed. So it's like they went to kick this bar this way, and as soon as they applied pressure, it's almost like kick as hard as you can. And it's just like no resistance. You just go, right? So technically, if you kick as hard as you can, and you're not able to actually apply force to that arm, there's no torque developed, no force, but your intention to move fast activated the muscle in a similar way as if you actually was applying force. So when you think about Olympic lifts, have you ever tried to do an Olympic lift slowly? A snatch, a power clean. Who can get under the bar if you do it slowly, right? You literally cannot do an Olympic lift or power activity slow. You ever try to jump slowly? I'm not leaving the ground. Right? White man can't jump. I'm only halfway, so I can deal with that. So anyway, that was a movie. That wasn't a anyway. But the idea here is that you can't do high velocity, high power activities or movements if you try to do them slowly, right? You can't. It's not possible. But the idea is if you intentionally move fast, that actually activates the muscle neurologically in a similar way as if you were actually applying force. So where is this important? Because they've actually done studies where we think about elderly people and we say, oh, they're elderly, they're frail, they're weak, they're very delicate. You can't train them very hard. And so we get into this concept about we need to train elderly people very slowly, very easy, Tai Chi's great, but when you're lifting weights, you want to be able to develop power and force, right? So we get in this habit of having elderly people do things slowly and controlled. But there was a study done a few years ago, and they've actually repeated this several times since then, that they told the elderly people to do the workout, do each contraction with maximum concentric velocity. So do the eccentric motion as you normally would, but when you go up for bench press, shoulder press, leg press, knee extension, squat, try to do it as fast as you possibly can on the way up, right? So we're telling them to intentionally move fast. Control group versus velocity group, same loads, right? Same rep scheme. The only thing different was they told the velocity group to move faster through the range of motion. And guess what? That resulted in greater increases in strength and greater increases in muscle size, better changes in functional movements like the sit and stand, like balance and agility, those types of movements you would test in elderly people, just by telling them to move faster during a resistance exercise repetition. Right? So in some ways, we might actually be doing a disservice if we're treating elderly people by saying, you have to lift slowly, you must do this tight and controlled. Yes, you want to make sure the technique's appropriate, but if they're able to, they're balanced, they have good coordination, they have no ligament or tendon injuries or muscle, things wrong with them, and they can actually do the movement correctly, it's actually okay to encourage them to maybe try to move faster, because if you try to move faster, there's greater level of intention, right? And by intentionally moving faster, greater force, greater muscle neural drive, better adaptations, okay? Does that make sense? So yeah, this was a study that showed that, yeah, even if you didn't actually develop force in the muscle because it moved so quickly, neurologically there was still muscle electrical signals, amplitudes, activation in those muscles, despite the fact that you didn't actually develop force. Which is interesting, right? Because this shows that even if you use the same load, but you just think to move faster, better muscle activation. So besides just thinking, contract as hard as you possibly can, it's like contract, muscle, mind, muscle. Oh yeah, good workout. You don't have to do that, you can just do it faster, right? And that's also an effective way to activate the muscle as well. But yeah, so thing here, the isokinetic versus isometric, they showed that whether you actually develop force in a muscle or not, so remember this side was they developed force, the other side they didn't develop force because they moved too fast, right? But at the end of that training period, you saw similar changes in force development across the entire range of the load spectrum, which goes to show that even if you didn't actually develop the force, the muscle kind of remembers how to move fast through those movements at the different loads, okay? So it has some training applications through there. So before, when I had talked about action potential amplitudes, right, we said when their depolarization occurs, it goes down the axon, motor end plate, acetylcholine receptors, back on the sarcolemma, T-tubules, release of calcium, cross-bridging, right? As the action potential goes along the muscle fiber across the sarcolemma, there's depolarization occurring there. So here's a muscle fiber, right? Here's the axon, here's the motor end plate, innervating, right? They go electrical, here's the amplitude, right? To chemical, back to electrical, and then here's the T-tubule, the sarcoplasmic reticulum. Remember, we have the dihydropyridine receptors that interact with the ryanodine receptors, release of calcium. As this action potential goes down along the sarcolemma, right, that action potential goes down to the T-tubules, results in release of calcium. So when you have the EMG sensor over the muscle, when it looks at EMG amplitude, it's looking at the overall electrical activity of the entire muscle, okay? But remember I said the decomposition system looks at that entire activation and pulls out the individual firings, right? So what it's doing is, it's actually, even if the entire signal looks like this, it's actually able to sense and see the individual firing or amplitude along that motor unit in those fibers, because it's sensing the amplitudes on the fibers. So what does that look like? That sensor, if you look under the sensor, right, you put it on the muscle, if you look under the sensor, there's some metal prongs, some metal pieces, right? The metal pieces are like electrodes, and they sense the position on the electrode of the electrical activity. So when you look at the amplitudes from the decomposed signals from the electrodes, you'll have channel 1, channel 2, channel 3, channel 4. It's measuring the electrical activity from each of those electrodes, points on the electrode. when you talk about amplitude, it's like the size. So in motor unit 20, which turned on during this contraction that went up to maybe 90% MVC, this was how motor unit 20 was firing. This is what the electrode picked up from each of those channels. Essentially, it averages the size, the peak-to-peak amplitude of each of those channels. You average it together, and then that is your motor unit action potential amplitude, right? It looks like that. That's the average size. What we see is that motor units that are larger have larger amplitudes. Motor units that are smaller have smaller amplitudes, okay? In this study, they wanted to try to use action potential amplitude as a non-invasive of motor unit specific hypertrophy, right? It's non-invasive. So they had already resistance trained people do resistance training for 8 weeks. They looked at their muscle size via ultrasound. At the end of 8 weeks, muscles got bigger and muscles got stronger. So resistance trained people do heavy resistance training, they get bigger, they get stronger. When you look at the motor units, their action potential amplitudes and the forces that they turned on at, we can see this dashed line is pre-training. So we can see that a motor unit that turned on at 5% of MVC had a small action potential amplitude. The motor unit that turned on at 50% MVC had a bigger amplitude compared to this one, but it had a smaller amplitude compared to the motor unit that turned on at like maybe 80 or 90%, right? So we see that, if we look at this dashed line, there is a linear relationship where the motor units that turned on at higher intensities, they're higher threshold motor units, correct? The motor unit turns on at a higher threshold, it's a higher threshold motor unit, right? Higher forces. So we can see higher threshold motor units have larger motor unit action potential amplitudes. However, after 8 weeks of training, this solid line, we see that there's a similar pattern up until around 50% MVC. After that point, we see that the motor units that were recruited after 50% MVC, their amplitudes get exponentially larger. These were already resistance trained people. So earlier when we said, oh, if you're resistance trained, if you're untrained, one way you can increase muscular strength is by getting bigger fibers or by recruiting more motor units, right? Motor unit recruitment. These were already trained people, so they likely were not recruiting more motor units because they already had that training adaptation, okay? But we saw they got bigger and they got stronger. But why do you think, like, if this is a linear relationship here at these lower intensities, but then something after 50% MVC, those motor units have now gotten larger amplitudes, okay? Remember we said that larger motor units have larger amplitudes? Did we say why they have larger amplitudes?
Just because of like more fibers and they're bigger, so they can.
Well, one thing is that those larger amplitudes, because they're innervating more fibers, okay? But those fibers are also,
High threshold.
well, they are for high threshold, but what's the quality about those fibers in high threshold motor units or high force motor units? We know they contract fast, they're probably touchy, but something about the size of the fibers.
Oh, they're bigger.
They're bigger. Remember we said the action potential comes down, depolarization, right? Amplitude goes across the sarcolemma down into the T tubules, right? Low threshold motor units, they have small fibers, so the amplitudes are small. Larger motor units have larger amplitudes because the fibers are larger in those motor units. So, if these are the same people and they're not recruiting more motor units because they're already trained, why is it that the motor units recruited up here have now suddenly gotten larger amplitudes? What might have happened? Yeah.
Did they pick up a heavier weight?
I'm sorry?
Heavier weight?
They were stronger, but it was still the same motor units activated. So because it's activated at the same relative intensity, it's still the same motor units turning on. They're just stronger for some reason. But why do you think that might be? Increase in size. Here we're saying small motor unit, large motor unit. Type 1, type 2. Larger motor units have larger amplitudes because they innervate bigger fibers. But what if I said this is pre, this is post? Smaller fiber gets bigger amplitude. So, that still doesn't explain though why there's even if the fiber's gotten bigger, that still doesn't explain why these ones got really big and these ones did not. There's still a motor unit, right? Motor units. But why is it that these ones have gotten larger to resistance training, but these ones have not? Can anybody think of anything? Mark?
Does it have to go like the whole thing you're talking about last lecture, where it's like basically the fiber will only activate to the intensity that's required. So as you start to increase that intensity, you'll get more activation of that same fiber.
Yes. Right? Resistance training. Well, if we look at intensities, contractions, we're all here, right? There's literally 0% MVC. Your muscles are not resisting anything. You get up, pick your backpack up, you walk across campus. If you're looking at the VL, what percent of your MVC is activated? Maybe not even less than 10%, small. You go to walk up to the stairs to the library or to some other building that has stairs, right? Maybe with your backpack, maybe you're now 20%, right? Activities of daily living are very low intensity, they're activating low threshold motor units, right? But those motor units are more oxidative. They aren't going to fatigue. They're going to be able to do those activities all day long. But resistance training, those are heavier loads than you normally do every day, right? So resistance training probably targets more of which types of motor units, if it's heavy. More of the higher thresholds, which are probably more 2As and 2Xs, right? So if we look at 50% MVC, if these are the motor units typically on during the day that are probably already trained from their activities of daily living, they're already trained people, maybe they're already of that size, when you have them do a new higher load resistance training program, now we're targeting motor units that probably don't normally get turned on, which are these higher thresholds. Type 1s and type 2s, they differ in size, yes? But guess what? Type 2s are also better at growing, right? Type 2s, they grow much larger than type 1s because they respond to stimuli to make them grow bigger. So these motor units out here are going to have larger amplitude sizes greater than the motor units down here because it's likely these fibers in these motor units have a better potential for growth. Which goes back to the fact of maybe this is a good methodology to test motor unit specific hypertrophy because let's say you're an elderly person, you go in for rehab and you redid your knee. You want to say, is this training program a good training program to rebuild the higher threshold or the type 2 fibers in your VL? How do I know that? Well, if we want to look at type 2s, you have to go in, do an incision, do a biopsy, get their muscle. Takes you months to analyze it, and then you know, okay, that's their fiber size. You have to go do invasive measures to measure the muscle fiber size, right? But what if there was a way to non-invasively do that? You could just measure their activity, measure the motor unit sizes, the amplitudes of those motor units, have them do a training program, and if you see that the amplitudes of those motor units changed in size, then you, especially if they're at the higher load contractions, then you can say, well, this was a good resistance training program because it probably caused the hypertrophy of these higher threshold motor units. How would you know? You look at the amplitudes, if the amplitudes changed, right? If the amplitudes didn't change and they're the same size, it would suggest then it didn't really target the growth of those higher threshold or type 2 motor units. But if the amplitude did change at those higher loads, that might suggest that those fibers did grow. And you didn't even have to do a biopsy. It was done non-invasively, right? So this avenue of like looking at amplitude sizes and how they recruit at different types of intensities is a good technology to be able to get accurate and applicable information very quickly that actually has some meaning, right? So you know, the elderly person in training is not effective, well, now we can say, oh, well, maybe we need to change how we're doing the training or switch up the training program versus sending it out to do a muscle biopsy, then taking months to analyze it, get the information back, right? It's a much more complicated process versus sticking an electrode on someone, getting an answer, training, getting an answer, all right? So, to reiterate, the next few slides are pretty important for your exam. You're gonna get asked questions about the relationships between the action potential amplitude, motor unit firing rates, and the MVC recruitment thresholds. Yes?
So the low threshold type 1s didn't grow very much, right?
Yeah, this says that the motor units that were recruited at lower thresholds of force, generally the amplitudes didn't change, which would suggest that the fibers in those motor units did not hypertrophy that much. So when we look at this graph that says, when they looked at the size of the VL, the muscle grew. But what this would suggest is that probably there was more hypertrophy of the type 2 or the higher threshold motor units compared to the type 1s. And that might actually make sense because the type 1s, if you're already resistance trained, you probably already got the fiber size adaptations in the type 1s already, right? And type 1s don't grow very much compared to type 2s. They still grow, but not as to the same degree as the type 2. So that kind of makes sense there. So, if you look at this contraction, they did a contraction up to 70% MVC. How do we know that? We look at the axis over here where it says MVC, percent MVC. We see that the plateau was upwards of around 70%. So this is a 70% contraction. They produced force, they maintained force, and then they released force. So if we look at these individual motor unit firings, we have motor unit number 3, which is dashed, and then motor unit number 10, which is the solid gray. We can see that motor unit number 3 is a low threshold motor unit. How do we know this? Because it turned on here at about 8 seconds in the contraction, or into the plateau. It turned on at, well, it's early recruited because it's 8 seconds, but it's low threshold because it turned on at 10% of maximum force. This motor unit number 10 is a higher threshold motor unit. How do we know that? Because it turned on at, look at the force tracing, around 70% MVC, right? So how do we know what force it turned on at? You just look at where it turns on and then where's the force tracing. Turned on here, the force tracing here was 10%. This turned on here, the force tracing suggests it turned it on at 70%. This motor unit in the middle turned on here, it probably turned on at around 40%, 35, 40%, okay? So, we're seeing low threshold motor units, high threshold motor units. What do we notice about the firing rate patterns of these motor units?
As you increase intensity, they go up with higher amplitudes.
Yes, in all of these motor units, as you need to produce more force, all of the motor units increase their firing rates. Okay? As you need to maintain force, the motor units maintain their firing rates. Obviously, there's some variability in there because there's fatigue and whatnot. And then as you need to produce less force, the motor units decrease their firing rates. We also see that as we need to produce more force, more motor units turned on. So we recruit more motor units to produce more force, and any motor units that turn on, are on already, they fire faster. Okay? When we look at the action potential amplitudes, the dashed line is motor unit number 3, so it's a low threshold motor unit. We can see that this has a lower amplitude or smaller amplitude compared to motor unit number 10. Solid line, right? Much larger amplitude, action potential amplitude. Again, another area on the electrode. Motor unit number 3, very small amplitude. Motor unit number 10, very large amplitude. Okay? Remember, the larger amplitude is because there's a larger amplitude sent along the fiber because it's larger. Smaller threshold motor units generally innervate smaller fibers, so they have smaller amplitudes. Okay? This is really important for your exam because I asked you probably about 4 different ways about the relationships between firing rates, recruitment thresholds, and action potential amplitudes. You have to know the terminology for all of them. So if I say this is a low threshold motor unit, you've got to understand that it turns on at a low threshold of force. And then I say, well, what is its firing rates at this type of intensity? If it's a low threshold motor unit and I'm asking you to describe its activity at 100% contraction, well, it probably has a really high firing rate, right? If I'm asking you to describe a high threshold motor unit at 90% MVC, it's a high threshold motor unit because it's turned on at 90%, but it probably has a low firing rate because higher threshold motor units have lower firing rates. So you've got to know those relationships. If I said an early recruited motor unit, that probably means it's lower. If I say a later recruited motor unit, it's probably a higher threshold motor unit because we know that if we need to produce more force in a contraction, if we're producing more force, that happens later, it's a later recruited motor unit. It's a higher threshold motor unit. So if we look at these relationships here, we see that the low threshold motor unit has a small amplitude, action potential amplitude. A high threshold motor unit has a high action potential amplitude. Look at the numbers. Motor unit number 3 has an amplitude size of 0.2. Motor unit number 10 has an amplitude size of 0.8, almost 4 times as big. Right? This amplitude is 4 times as large and a larger motor unit. Okay? Also notice this motor unit turned on at 4 times the amount of force compared to motor unit number 3. Right? 10% versus 50%. Much higher. So the higher the load, the higher the force, the more likely you're going to recruit a motor unit that has a bigger amplitude. And the amplitude is larger because it's innervating more fibers and those fibers are bigger. That relationship is consistent. We also see that motor units that have a smaller amplitude in general have faster firing rates. Motor units that have a larger amplitude generally have smaller firing rate or slower firing rates. Remember, a larger motor unit, if it's innervating more fibers and those fibers are bigger, if you have those units contract at the same time, this bigger one is going to produce more force. So it doesn't need to fire as fast because every time it fires, it produces more force than the one that's smaller and firing very frequently. All right? So larger motor units fire less frequently, but they produce more force. And then the original relationship we saw, recruitment threshold, firing rates. A motor unit that turns on at a lower threshold of force, they generally have higher firing rates. Motor units that turn on at a higher threshold of force generally have slower firing rates, okay? If we look at this dot here, motor unit number 10, this contraction was only 70% MVC. How do you think this dot might move if they did the contraction up to 100% MVC? Where do you think this dot, would this dot go up, down, left, right, what would happen? It would go up, right? So if this contraction is 70%, and this is how fast it was firing, then if this motor unit was on and they needed to produce more force and went up to 90%, it would go from 10 pulses per second to maybe 12 or 13 or 15 pulses per second. It would go up. Its firing rates go up as you need to produce more force. Remember the pool analogy, right? This threshold of force turns on these motor units, but not those. You increase the force level, the ones that are on fire faster, and then the other ones that are now stimulated, they start to turn on. Okay, so that pool analogy is really important to remember, like the threshold of force and then their firing rates, how they behave in that way. Okay. Now, when we look at resistance training, in this study they had 2 groups. They had a resistance trained group and then they had an untrained control group. The resistance training group, they had on average 5 years of resistance training history. Okay, so they weren't people that just trained for the last 3 months and now they're trained. They had actually been training for the last 5 years. They could squat at least 1.5 times their body weight. They were squatting consistently for at least once a week for the last 2 years, right? So they were training these muscles, okay? But if you think about those training statuses, trained versus control, okay, we know that generally resistance trained people are bigger, they have larger muscle mass, and they're stronger than untrained people, okay? So keep that in mind. I'm not showing you that result here, but in this study, the resistance trained people were bigger and were stronger. So a resistance trained person, is their 20% of their MVC, is that more weight or less weight compared to an untrained person? more weight. Even though it's the same relative intensity, 20%, because the trained people are stronger, they're actually they're resisting more weights, right? So keep that in mind as we're going through these results. So you have two different contraction intensities. One was 40% MVC, the other was 70% MVC. What do we see? There's not much difference in the firing rates and recruitment thresholds at the higher intensities. The slopes respond pretty similar between those two groups. All right, so they didn't see a difference at 70% MVC. But when we look at the firing rate behavior and the recruitment thresholds at the lower intensities, the 40% contractions, we see there's a difference in how the motor units were behaving between the two groups. So in the untrained group, let's say at 20% MVC, right, the entire contraction went up to 40%, right? But let's look at the motor units that were turning on at 20% MVC. In an untrained person, these motor units were firing faster than the group that was trained. So the trained group, at the lower intensities, their motor units were firing slower compared to the group that had no training. We also see the motor unit action potential amplitudes. The untrained people, when they did contraction intensities up to 40% MVC, they had amplitude sizes of the motor units were larger compared to the motor units in the trained group, right? So what do we know about action potential amplitude sizes and firing rates as force production? What do we know, what happens there?
Bigger size, bigger amplitude.
So if the amplitude sizes are larger, you're probably recruiting more motor units, right? If the motor units are firing faster, what does it tell you about the difficulty of the exercise?
It's hard.
It's harder, right? This says that these motor units are firing faster. They're working harder to produce this force, okay? But, so that would suggest, okay, well, the untrained people, they have faster firing rates, they have larger amplitudes of motor units turning on, they must be producing more force. But, remember I said, these were resistance trained people. They were stronger. They were bigger than the untrained people. So, why is it that the untrained people were producing less force, but yet their motor units were firing faster, and they were recruiting motor units with bigger amplitude? What does that tell you about the differences between the training statuses?
They had to recruit more fibers, and those fibers would have less force, so that's why they had to recruit more.
Yeah. How do we know that these untrained people had to recruit more fibers? Because when you look at the amplitudes of the motor units they were turning on, those motor units were larger, right? Remember, smaller motor units are typically recruited first. There's smaller, less force, less. If you need to recruit larger motor units at this intensity, that would suggest you need to recruit more motor units to get that force done, right? And also the fact that these motor units were also firing faster. So despite the fact that the untrained people were using the same relative intensity, at lower loads, lower absolute loads, their muscles were firing faster and they were recruiting more motor units to do less work. So if the resistance trained people had lower firing rates, how can they produce more force if their muscles are not firing as fast? Right? We know that they're stronger than the untrained group, but they're not getting that additional strength from the motor units firing faster. So where is that force coming from?
It's just a bigger motor unit, so it can just generate more force.
Well, it's not a bigger motor unit because if we look at the size, it's actually small, right? The motor unit itself is smaller, right? It's a smaller size motor unit. But what does that tell you about its ability to produce force? Because remember, the size of a motor unit is two things: the number of fibers it innervates and
The size of the fiber.
the size of the fibers, right? That allows it to produce force, right? In general, larger motor units innervate bigger fibers, and those fibers, more fibers, and those fibers are generally bigger. The smaller motor units, they innervate less fibers, but what if those fibers got bigger? Would they produce more force? Is there a relationship between force production and firing rate? If we think about high threshold motor units and low threshold motor units, the high threshold motor units, they fire very fast, but they produce more force, which is why they don't fire so fast. The low threshold motor units, they fire faster, but they need to because they don't produce much force when they fire. So if we look at this, in the trained people, their motor units are not firing as fast as the untrained people, but they don't need to fire as fast because the fibers in those motor units have grown, hypertrophy. They fire, but they produce more force per twitch because they have 5 years of training history. The fibers, these low thresholds have gotten bigger, so now they produce more force every time they fire. And also, we don't need to recruit as many motor units to do 20% MVC. Because, how do we know that? Because the size of the motor units being recruited are still small in size. Right? Small in size because they're not innervating many muscle fibers, but the fibers they are turning on are bigger. So what does this mean? This means that with resistance training, you actually don't need to recruit as many motor units to produce the same relative force. Imagine if you were resistance, it's kind of like the crossover concept with like carbohydrate use in training, right? When you're untrained, you use a lot more carbohydrates earlier compared to the trained state, right? So if you had to increase intensities, trained and untrained, the untrained person is going to run out of carbohydrates faster because they've used all those substrates a lot faster. They're very limited in its source. But a trained person, they're going to have more carbohydrates in their muscle because they use more fats better, right? Here, a resistance trained person doesn't need to recruit 2As or 2Xs or even big 1s or 2As to do this amount of work to produce this force because the fibers that are here are already making up for the force because they're bigger, right? There's no need to recruit more motor units if the motor units that are turning on are already large and producing enough force to begin with, right? In some ways, it's almost glycogen sparing because if this is let's say it's a type 1 muscle fiber, right? Ordinarily, if you needed to produce more force, you'd have to start recruiting more motor units that probably have more glycogen in them. But if these motor units are oxidative and they've gotten bigger, now you can produce more force with an oxidative fiber. It's not going to fatigue as fast, which means you don't need to tap into glycogen as much, right? Which kind of spares that. So the idea is that, like, why does resistance training, when you get stronger, why does it get less stressful? Well, because you get adaptations. One adaptation is the fiber gets bigger, so it literally makes that submaximal load easier to perform because the fibers have gotten larger in those smaller motor units, okay? Does that make sense? Yeah, so, but this happens with chronic training, okay? What happens with short-term training? In this study, they had untrained people do just 8 weeks of training. Again, they looked at relationships between recruitment threshold, firing rate, recruitment threshold, amplitudes, and firing rates. We see the same relationships again as all the other slides. So we've seen this relationship 4 times now, and we're still seeing consistent properties. Again, smaller motor unit, smaller amplitude. Larger motor unit, larger amplitude. Motor unit number 4, motor unit number 18, they did this contraction up to around 70% MVC. What do we see? Following only 8 weeks of training, they didn't see changes in they did see changes in the amplitude sizes in the resistance training group, but they saw them particularly in the larger threshold motor units. So just like that other study that showed the non-invasive measure of hypertrophy, with, it was linear and then the post-training was exponential, we're seeing the same thing. Very similar sizes in the amplitudes in motor units that were recruited less than 50%, but notice how as we get to higher intensities, this line starts to become more divergent, very similar to the Pope article. So it suggests that resistance training particularly stimulates the higher threshold motor units. That makes sense. You turn on those motor units to produce more force. Resistance training is high force. That makes sense. But what about the motor unit behavior? We see that the amplitudes got larger, that would suggest that the fibers in those motor units got bigger, right? Muscles grew. That's what the amplitude changes would suggest. But did the behavior change? When you look at the firing rates of the high threshold motor units and the low threshold motor units, what do we see? There's not much of a difference in the firing rates of the low thresholds, right? The previous study, they showed that at the lower intensity, they had lower firing rates compared to the untrained people. So if we look at this pre and post training study, we'd suggest, oh, following training, the firing rates of this one should be slower because fiber is hypertrophied. But in fact, what do we see? If you look at the amplitude of these low threshold motor units, are they kind of the same? Yeah, so this resistance training program didn't really hypertrophy the low threshold motor units. How do we know that? Because the amplitude sizes didn't really change. And if the amplitude sizes didn't change, that really had no result on changes in the firing rate of the low threshold. So we're not seeing the same result as a previous study in chronically trained people because this is only short-term training. However, if we look at high threshold motor units, again, we see the firing rates are not different between pre and post training, but we see the amplitude sizes have changed, right? The solid line is the pre-training, the dashed line is the post-training. So this suggests that in short-term training and untrained people, resistance training hypertrophies the higher threshold motor units. How do we know that? Because the amplitude size of specifically the higher threshold motor units got larger. We can look at this on the graph. Pre-training, post-training. No difference in the overlap at the lower loads, lower threshold, but there was a very big difference at the higher thresholds of force. And that's reflected here. If you look at this motor unit that turned on at 65% NVC, pre-training and post-training, they're firing very similarly, but the size of that motor unit is very different. So if you had a motor unit that's firing the same, but it's got a bigger amplitude, what does it tell you about its force production? Probably higher, right? So resistance training is going to allow you to produce more force because the fibers get bigger, at least in short-term training. Yes, you do recruit more motor units with training, that's true. But also, the fibers get bigger, particularly in the higher thresholds, which allows to produce more force, okay? We're not really seeing much changes in the firing behavior of the low thresholds with short-term training, but we do see changes with many years of training, okay? Unfortunately, there's not many studies out there that are really comparing very well-trained people to untrained people. So the few studies that are out there are kind of limited in scope. We've also got to consider, these are mostly isometric contractions. Would we see the same responses if they were dynamic? If they were elite athletes? We don't know, right? Because it's still an emerging technology, still an emerging area of interest, but promising or interesting results or similar interesting behavior to kind of take note of. So we're coming to the end here. So if we look at muscle fiber conduction velocity, okay, when we think about a contraction, okay, we have the action potential sent down to the muscle fiber, that propagation of that signal, release of calcium, contraction, okay? You have to have the action potential sent down to the motor end plate, and then that after the motor end plate, that action potential is sent along the muscle fiber, the sarcolemma. How fast it moves along that sarcolemma is called muscle fiber conduction velocity, right? The action potential is conducted, and how fast it moves is velocity. So when we think about like a race, okay, like the 100-meter sprint or dash in the Olympics, all the racers get down in the blocks, right? When the gun goes off, they jump out of the blocks, okay? Usually, the sprinter who gets out of the blocks the fastest is probably the more powerful one, the more explosive one, right? They're able to produce force faster, get out of the blocks and run, get ahead quicker, right? Now, who knows about the end of the race, but at least at the start, that means they're more explosive. When you look at contraction, the application of force, the rates of torque development between trained people and untrained people, if you have them do a specified speed of contraction, the trained people are able to apply more force at the very, very, very start of contraction compared to the untrained people, right? So when you think the initiation of force, right? When you first start the contraction, trained people are able to apply a lot more force quicker compared to someone who's not trained. Now, later in the contraction, the application of force appears to be pretty similar. But the initiation of that force, the first rates of torque development, the very earliest window, earliest application is highest in trained people. And why is that? Because when you look at how fast that conduction velocity along the sarcolemma of the muscle, how fast does it move between trained and untrained people? The action potential is moving slower in untrained people at the start of the contraction. In trained people, that action potential gets to the muscle faster, which results in them applying force faster. So literally, it's like, why do trained people, why are they more powerful? Why are they more explosive compared to untrained people? It's not just because they have bigger muscles. Literally, the nervous system and the electrical discharge of that action potential to the muscle happens faster. So if the action potential is happening faster, they can develop force faster. That results in greater power and explosiveness as it translates to performance, all right? Now, this study hasn't been done in humans, to my knowledge, as of yet, but they actually looked at neuromuscular branching in the motor end plate. So you know how the axon goes to the motor end plate, its branches to the muscle fibers and things like that. So in this case, they had rats do low load resistance training, and then they had them do high load resistance training. And so these black squiggles are the nerve branching at the motor end plate, the nerve branching there. Then the white part is the acetylcholine receptors. So you can see that when these rats did heavy load resistance training, there was more nerve branching and more innervation with acetylcholine receptors with the heavier loads, right, compared to the light loads. Now, in the actual study, both groups of rats, they lifted weights, they both got stronger, but the group that did the heavier loads got stronger than the group that did the lighter loads. And one of the reasons that might be is because maybe there's more nerve branching between the fibers and innervation of the fibers and the axon that might result in better conduction velocities or more efficient recruitment of those muscle fibers, potentially, right? But this might be one of those mechanisms that supports why heavier loads produce better adaptations in strength compared to lighter load resistance training, right? Not done in humans yet, but an interesting, at least physiological model to study that might allude to one of those mechanisms. And then lastly, if we look at how motor unit behavior or motor unit qualities change with aging, okay, if we look at the neuron here and its innervation with the fibers, okay, the red are going to be the oxidative fibers, the blue are going to be glycolytic fibers. So if the blues are type 2s and the reds are type 1s, we can see that in young muscle, when you look at fiber types, they're pretty much mixed heterogeneously throughout the muscle, the entire muscle, okay? You're not seeing groups of 1s and groups of 2s. They're kind of all mixed in collectively the same. But we can see that as we start to age, like 60 to 65 to 70, notice how now we have some bundling, some grouping of these muscle fiber types. Notice how we have more type 2s here and we have more type 1s here. Right? It's not a heterogeneous mix like we see as we're younger. Okay, and what happens is as we age, if we're not activating those higher threshold motor units, those type 2 motor units, if we're not activating them, it actually causes the neurons to die. Okay, so if you're younger and you're sedentary and you're not activating those type 2s, well, they're just not getting activated, right? You're young, you're not stimulating those neurons. But as we age, if those neurons of the type 2s aren't getting stimulated, the neuron actually dies. Okay, so if the neuron dies, but the fiber still stays, what do you think happens?
It starts to degrade.
Actually, that fiber now becomes innervated by a type 1 neuron, right? So why do we get a shift? See here, they're mixed in heterogeneously. As we age, now we're getting some grouping. And when the neuron dies, now we actually have less type 2s and more type 1s. Why is that? Because when the neuron dies of a high threshold motor unit or a type 2 motor unit, that fiber actually gets innervated by a type 1. Now that type 2 fiber becomes a type 1 fiber. Remember, did I tell you guys about the cats and the switching of the muscle fibers? Right? You have a fast twitch neuron innervating a fast twitch muscle. They had the slow twitch neuron innervating the slow twitch muscle in cats. Then they swapped the neurons. So they had the fast neuron then swapped and is innervating the slow muscle. And they had the slow neuron innervating the fast muscle. What do you think happens to the muscles? Switch the muscle type, right? The muscle fiber types are determined by the nervous system input, right? None of us are out here are changing our type 1s to type 2s because our nervous system is pretty much laid down genetically, right? We're not choosing to have more 1s versus 2s, it's just we're born with it. Okay, so the muscle fiber types are primarily genetically determined. Obviously within the 2s, you can shift from X to A, there's shifting going on. But from the 1s to the 2s, you don't see as divergent or very common shifts between those because the property of the neurons are actually pretty different. Right? So if you look here, what used to be a high threshold, high force producing fiber now becomes an oxidative, low force producing fiber because it's innervated by a type 1. And it was only innervated because it lost the neuron of the type 2 or the high threshold. And we lost that neuron because we weren't stimulating that neuron. What's the only way you can really stimulate a type 2 or a high threshold motor unit? Higher loads, right? So if you're sedentary as you age, you're not going to be stimulating those neurons that are only activated with higher loads. This is why it's extremely important. I mean, us maybe, generations are different than maybe our grandparents and great-grandparents, even our parents to some extent, right? Depending age range in here, right? But if we think about like the culture around lifting and exercise, particularly for women, right, it's more accepted to lift weights now. It's more accepted to exercise, right? More men exercise, more men lift weights, more women lift weights. So I don't think it's as much of a hindrance in society now as compared to like our elders in terms of like going and lifting weights or the importance of. We see a lot of elderly women with osteoporosis. Why is that in poor bone health and bone disease? Why is that? Because women shouldn't lift weights. It's too manly. You'll get too big. The fact they weren't lifting heavy resistances, they developed poor bone mineral density. So as you age, you lose that bone. Osteoporosis, fractures, leads in the hospital, injuries, it's all downhill. So now we say you should be resistance training. You're going to build that bone mineral density, and the more you can build when you're younger, the better you'll be able to have when you're older. But also keep in mind too that as we age, it's not just about building the bone mineral density and the muscle health. You want to be able to continue to load that muscle as we age because that's going to preserve the health of those higher threshold motor units, those neurons. Think about it. When an elderly person gets injured and goes to the hospital, what's one of the more common injuries that they end up going to the hospital for? I'm sorry, a hip fracture. Fracture, broken bones, torn ligaments, things like that. Part of that happens because, one, a balance issue, right? The other is like, okay, even if you had a poor balance issue, if you had the coordination to catch yourself from the fall, that would be a good thing. When you go to catch yourself from a fall, is the movement fast or slow? Fast. Which motor units are getting activated? Type 2s, right? So to recover from a potential fall, you need to have those fast contracting muscle fibers to contract quickly to catch yourself. And then when you think of an eccentric load, is this a light load or is it an accentuated load? It's heavier, right? So now you need those type 2s to stand that extra weight from this extra loading from this trip, right? Imagine you haven't trained your high threshold motor units. You've lost the type 2s, you cannot catch yourself in proper position, you fall, break your hip. Or you do catch yourself, you don't have the muscle strength of those high thresholds to resist that force. So you catch yourself, but you fall and still injure yourself, right? Once you're in the hospital, you immobilize, more muscle loss, more coordination deterioration, you're sedentary now, broke your leg, comorbid conditions. It's like they've shown that as you age, the likelihood of you successfully aging or the absence of diseases as you age is better the longer you can keep yourself out of the hospital. Okay, so the longer you can prevent yourself from having an extended stay in a hospital as you age, the more likely you're gonna be able to live longer and live healthier. Because when you have an extended stay in the hospital, you're bedridden, you lose muscle mass, develop insulin resistance, and all these other factors kind of contribute to poor quality of life, less activity, more injuries, and so on and so forth. My great grandmother, she fell on the stairs and broke her hip, and then from there it was just, I was really young at the age, but I can still remember my parents and grandparents talking about in the hospital again, right, more deterioration of health just by that one initial incident, right? So how can we prevent that? We should encourage our grandparents, our parents to get in there and lift weights. It's never too late. And I don't mean go in my kitchen and lift Campbell soup cans. No, that's not heavy enough, right? I'm gonna lift some water jugs and just walk around the house. No, you need to be like, you should have put a backpack on, maybe load some weights, go to the gym. I mean, there are cases where you can go to a recreational gym and there's specials for elderly people to be active, but the idea is they should be getting there and be doing the leg presses. You don't have to be doing squats and lunges, but you need to be activating those muscle fibers in a sufficient way to maintain the health of the neurons and the fibers. Because if you can maintain the health of those fibers, you are going to be able to prepare yourself better for advertent events later on in life, right? So we want to maintain the size of the muscle, better quality of life, prevention of falls and fractures, right? And good for insulin resistance, caloric expenditure, right? So all those things collectively are going to be good for us, but we have to remember to train and make sure we're lifting weights. So I think we're kind of okay with the lifting weights, but it's even your parents and grandparents might even suggest, hey, let's go to the gym. I'm going to show you a few things. And sometimes it's like, well, what do I do? How do I do this? What do I do? Well, that's where you guys come in, right? This is your specialty, applied fitness, exercise science. You have the knowledge. You know how to train them. Reps and sets, rest periods, what types of exercise, progression. This is what you're getting your degree in. So it could have a meaningful impact, not just for you, but for your family in the long run by educating them on that, right? And that's the whole point around health and science and all that kind of stuff, right? Because you can make those small differences. But encouraging the people in your lives, especially if they're older, to lift, and if they are lifting, to continue lifting is going to be really important. Yes, Mark?
Talk about how that 2B will turn, or that 2 will turn into a 1. Can it go back, or is that just?
Nope. Once you lose that type 2 neuron, it's gone. Right. The thing is, though, just because you lift weights doesn't mean, even if you're lifting heavy, that doesn't mean you're never going to lose a type 2 neuron. It's just a part of aging, right? You get older, you lose your anabolic potential, the cells die, neurons die, it's going to happen, right? But they have shown that if you're resistance training as you age, you lose less of the neurons compared to not exercising or lifting at all. So you're better off doing something than doing nothing, okay? And yeah, cardiovascular health is great. They should have some level of cardiovascular fitness, running and aerobic exercise is great, but what we see as you age, a lot of your quality of life is kind of like strength and size dependent. Can you cook? Can you lift your grandchildren up, right? Can you get up a flight of stairs with groceries? Can you grab pots and pans and move things up? You can't even eat sometimes because you have poor muscle health in your jaws, right? Because you're not used to eating and meats and stuff like that. So the whole process gets very complicated as we age. If we can maintain the strength and the size of the fibers as we age, it's more likely we can age successfully versus I just want to live till I'm 100. Well, who wants to live till you're 100 if you're 30 years in and out of the hospital, right? Lift weights, good. All right. So that's just a summary of that. So to be honest, we could end there today because I'm not going to start a new lecture. However, I'm not going to start with this new topic. We can just do that next week. I want to use this time that if you have any questions about the lab stuff, you can literally shoot me anything. We have 10 minutes here. Anything you want to know about the lab. Questions, concerns, something is not clear, insight, anything. I've gotten stuff from maybe about 25% of you, questions or reviewed your stuff, but some of you I haven't heard anything from, and I'm assuming you've been keeping up with the activities, you got the figures correct, the idea about writing is pretty good, but if you don't,